Hello and welcome. Today I will tell you 10 facts about Earth that you didn't know before. So get your snack and let's jump on it. First one, the purple Earth. The purple Earth hypothesis suggests that ancient microbes may have used retinol instead of chlorophyll to capture sunlight for energy. Retinol absorbs green light and reflects red and blue, which combine to give a purple hue. You may ask why retinol instead of chlorophyll. Here are 3 reasons why. Number 1. Early sunlight absorption. The green part of sunlight is the most intense, and retinol absorbs green light effectively, making it a good candidate for early photosynthesis. Number 2. Simple and efficient. Retinol is chemically simpler than chlorophyll and could have evolved earlier. Number 3. Survival in extreme environments. Some modern archaea, like halobacteria, still use retinol-based photosynthesis in extreme conditions, suggesting it could have been widespread in ancient Earth. And why did the Earth turn green? Over time, chlorophyll-based photosynthesis outcompeted retinol because it absorbs red and blue light, which is more energy efficient. And it also produces oxygen, which reshaped Earth's atmosphere and allowed complex life to evolve. So, if you had a time machine and traveled back 3+ billion years, Earth might have been a glowing purple planet instead of the green and blue world we know today. Second one, the day isn't exactly 24 hours. It's about 23 hours, 56 minutes, if we measure it by how long Earth takes to rotate once relative to the stars. However, we use the solar day, which is slightly longer. And why isn't a day exactly 24 hours? Because Earth's rotation is slowing down. The moon's gravity creates tidal friction, which gradually slows Earth's spin. Millions of years ago, a day was much shorter. For example, 1.4 billion years ago, a day was only about 18 hours long. Another reason is that Earth orbits the Sun. As Earth rotates, it also moves along its orbit around the Sun. To realign with the Sun after one full rotation, Earth has to rotate a little extra, making the solar day about 4 minutes longer than the sidereal day. And last reason, seasonal and planetary effects. The tilt of Earth's axis and gravitational interactions with other planets cause small variations in day length throughout the year. Over time, Earth's rotation continues to slow, meaning that in millions of years, a day will be longer than 24 hours. The third one, we are inside Earth's atmosphere, even in space. The statement refers to the fact that Earth's atmosphere doesn't suddenly end at a specific point, it gradually thins out, extending much farther than most people realize. And how is this possible? Earth's outermost atmospheric layer, the exosphere, extends hundreds of thousands of kilometers into space. In fact, some particles from Earth's atmosphere reach beyond the Moon. Layers of Earth's atmosphere and space are troposphere, that is where we live and where weather happens. The distance is from 0 to 12 kilometers. Stratosphere contains the ozone layer. The distance is from 12 to 50 kilometers. Mesosphere is where meteors burn up. The distance is from 50 to 85 kilometers. Thermosphere is home to the International Space Station. The distance is 85 to 600 kilometers. And finally, exosphere, and that is the outermost layer, where Earth's atmosphere gradually merges with interplanetary space. The distance of exosphere is 600 to 100,000 kilometers. The fourth one, deepest part of Earth's crust, is located underwater. It's because the oceanic crust is thinner and denser than the continental crust, allowing it to be pushed deeper into Earth's mantle at subduction zones. And how deep is the deepest part of the crust? The Mariana Trench, specifically at the Challenger Deep, is the deepest known point in the ocean, plunging about 10,994 meters. That's 36,070 feet or 7 miles below sea level. However, the crust beneath the trench extends even deeper. The oceanic crust here is about 5 to 10 kilometers or 3 to 6 miles thick. Beneath it is the Mojave discontinuity, the boundary between the crust and the underlying mantle. The total depth from the ocean surface to the bottom of the crust in subduction zones can be around 20 to 30 kilometers. That is 12 to 18 miles. And why is the deepest crust underwater? Oceanic crust is thinner but denser. The continental crust is about 30 to 70 kilometers thick, while oceanic crust is much thinner at 5 to 10 kilometers. Since oceanic crust is made of dense basalt, it sinks lower into the mantle than the less dense, granite-based continental crust. The fifth one, Earth has a huge underground ocean. Scientists have discovered that Earth has a massive underground ocean deep within the mantle, but it's not a traditional ocean of liquid water. Instead, the water is trapped inside a special mineral called ringwoodite. The underground ocean is located in the transition zone of the mantle, about 410 to 660 kilometers beneath Earth's surface. The water is stored within the crystal structure of minerals rather than as a free-flowing body of water. But how do we know it exists? Because of seismic waves. Let me explain this, guys. When earthquakes occur, their seismic waves travel through Earth. Scientists notice that some of these waves slow down in a way that suggests water-rich minerals exist deep in the mantle. And also, there is one more thing: ringwoodite discovery. In 2014, scientists found a diamond from deep inside Earth containing ringwoodite, a mineral that can hold water within its structure. This confirmed that large amounts of water are stored hundreds of kilometers underground. And how much water is down there? Some studies estimate that the amount of water trapped in these deep mantle minerals could be 3 times the volume of all Earth's surface oceans combined. Why is this important? This deep water may play a role in the movement of tectonic plates, volcanic activity, and even Earth's long-term water cycle. It also suggests that Earth's water may have originated from inside the planet, rather than just from comets. The 6th one, gold and other heavy metals rain down from space, but not in the way you might imagine. This happens through cosmic processes involving neutron star collisions, supernovae, and meteorites. But how is gold created in space? Gold is not naturally formed on Earth. Instead, it originates from violent cosmic events. For example, neutron star collisions. When 2 neutron stars collide, they create an explosion called a kilonova. This releases an extreme amount of energy, triggering the rapid neutron capture process, which forms heavy elements like gold, platinum, and uranium. These gold atoms then spread across space as cosmic dust. Massive stars that explode like supernova also create heavy elements. The gold and other metals from these explosions mix with interstellar clouds, eventually forming new planets and asteroids. But how does gold rain down on Earth? Asteroids and meteorites. That means ancient meteorites delivered gold to Earth during the planet's early formation. Cosmic dust. Tiny space particles carrying gold still fall to Earth daily, though in small amounts. And lastly, deep Earth deposits. Some gold may have originally come from these cosmic impacts and later resurfaced through volcanic activity. The 7th one, Earth's core is actually younger than its surface. Why is Earth's core younger? Because gravity affects time. According to general relativity, the stronger the gravitational field, the slower time moves. Since Earth's core is much deeper inside the planet, it experiences stronger gravity than the surface. But also time moves slower at the core. The intense gravitational field at the core slightly slows down time compared to the surface. This means that over billions of years, time at the core has been ticking slightly slower than time at the surface. Scientists estimate that the Earth's core is about 2.5 years younger than the surface. This might not seem like much, but considering Earth is 4.5 billion years old, even tiny differences add up. Real-life example of time dilation. GPS satellites experience the opposite effect. Since they are farther from Earth's gravity, time runs slightly faster for them than for people on the surface. Scientists have to correct for this effect to keep GPS systems accurate. Earth has an anti-moon, or rather, a quasi-moon called asteroid 2006 or H120. You are probably asking, what does anti-moon mean? Some people refer to quasi-moons or orbital asteroids as anti-moons. These are small space rocks that share Earth's orbit around the Sun but don't orbit Earth in the same way the Moon does. They appear to follow Earth and sometimes get temporarily captured by our gravity. 2006 or H120, or temporary mini-moon, or whatever you want to call it, was discovered in 2006. This asteroid is only about 2 to 3 meters wide. It was briefly captured by Earth's gravity between 2006 and 2007, making it a temporary moon before it drifted away. Why aren't these true moons? Unlike the Moon, which is gravitationally bound to Earth, these objects are actually orbiting the Sun and just appear to orbit Earth due to their unique motion. They come close and drift away over time, unlike the Moon, which stays in a stable orbit. So, does Earth have an anti-moon? Not exactly, but Earth occasionally picks up small temporary moons or quasi-moons that behave like companions before drifting away. They aren't true anti-moons, but they're still fascinating space objects. Next one. Earth is radioactively active due to the presence of naturally occurring radioactive isotopes. This radioactivity is a crucial factor in Earth's internal heat and geological activity. The primary sources of Earth's natural radioactivity are radioactive isotopes found in rocks and minerals. The most significant contributors include uranium, thorium, potassium. These isotopes undergo radioactive decay, releasing heat and particles over long periods. How radioactivity heats the Earth. When these isotopes decay, they release alpha, beta, and gamma radiation, which transforms into heat. This heat contributes to mantle convection, which drives the movement of tectonic plates. Volcanic activity fuels magma generation. And lastly, geothermal energy. This maintains high temperatures in Earth's interior. And why Earth is still radioactive? The isotopes mentioned above have half-lives in the billions of years. That means they are still actively decaying and producing heat. And last one is about that we still don't understand earthquakes. We cannot directly observe the deep layers of the Earth where earthquakes originate. The deepest borehole ever drilled only reached 12 kilometers, while most major earthquakes originate from tens to hundreds of kilometers deep. Scientists rely on indirect methods like seismic waves, but these have limitations. Earthquakes are chaotic and non-linear. The Earth's crust is made up of fractured, unpredictable materials under immense pressure. Small stress changes can trigger large quakes, similar to how a tiny push can cause an avalanche. This makes it almost impossible to predict exactly when, where, and how big an earthquake will be. We lack a reliable precursor signal. Unlike hurricanes or volcanic eruptions, earthquakes don't always have clear warning signs. Some quakes show foreshocks, but not all. Some involve changes in gas emissions or ground deformation, but these signals are inconsistent. No single pattern has been found that reliably predicts an earthquake. Is there ever a chance that we can predict earthquakes? Currently, we can only estimate probabilities, but not exact timing. AI and machine learning are being tested for finding new patterns in seismic data. Early warning systems can detect an earthquake seconds after it starts and send alerts, but they don't predict quakes before they happen. That's all for today's video. I hope you enjoyed this one, and if you did, please leave a like and subscribe. See you soon.